Hey guys, welcome back to the channel. Today we are going to discuss about one of the most common and most asked questions about distributed transaction happening in a big server in real-time environment. How do we do the locking? There is one solution that is very commonly used. It's called two-phase locking. So imagine two people trying to update the same bank account at the same time. Chaotic, right? So that's why the database used concurrency control techniques like two-phase locking. So in this tutorial, we'll cover some of the concurrency issues, what is 2PL, how it works, and some of the types of two-phase locking. They are like basic, strict, or rigorous. We'll take some examples, work on the advantages, disadvantages, and deadlock. By the end, you'll fully understand the two-phase lock and why it ensures serializability. So let's discuss about the problem which we have been facing before two-phase locking. Suppose there's a server A. We will mark this as server A and user A. He wants to append a value or maybe add a value. Let's say add a value. So he does plus 10. Then he's not over yet. He wants to do and read, and based upon the value he wants to do minus 5, then again read and want to do plus 20. Now user C, oops, wrong spelling, user C, we'll mark it as user A. Now the user C wants to read the value, the final value, which value it should be. This is the final value should be after plus 20. So it can either read after plus 10, it can read after minus 5, or it can read after minus 20. Now that's a problem, you know. These will be dirty reads. You won't get the most updated value and the value might suddenly change. So there's a problem in here. So how do we handle the scenario? The problem comes especially in the banking, you know, when you do a transaction, when there are concurrent transactions. Let me take a banking transaction. User A does plus $10. Then concurrently, user C does minus $5. Which scenario happened first? Plus 10 or minus 5? What if the balance was 0 and minus 5 happened first? In this way, it will go to minus 5 balance. And that is really wrong. The bank will be in loss. Although the user will be in a profit, he'll get $5. But that's not the case we're solving here. We're solving the concurrency issue. So this is where we start about two-phase locking mechanism. So let's discuss about the core concepts of two-phase locking. Okay. So the first concepts we are going to discuss about is locks. So in this case, we have two types of locks. One is shared lock and another is exclusive locks. We can mark shared lock as S and exclusive lock as X. So the definition of shared lock is that whenever we have a transaction in which we only do reads, in that case we use shared lock. We want to concurrently allow reading by multiple resources. So we can give a shared lock. This lock is shared by multiple servers. Then we have exclusive locks. Exclusive lock is primarily used when we want to write or update a thing. Now, whenever a transaction happening that involves writing or updating a value, in that case, we want to put an exclusive lock. And whenever the exclusive lock is acquired by any of the resource, all the locks are vanquished. Whenever there is an exclusive lock, mark my word, you cannot even give a shared lock to anyone or any other exclusive lock. That is the main difference between the two locks. That is, in shared lock, the locks can be shared and it's generally only for reading purpose. Whereas exclusive lock, it's only one. And once the exclusive lock is there, nobody can acquire a shared lock as well. Everyone has to wait till the time exclusive lock has been released. Now, let me take an example of how the two-phase locking integrates. So, we have two phases of two-phase locking. So, two phases. The first phase is growing phase, and the second phase is shrinking phase. Growing, as the name suggests, grows, and shrinking means shrink. So growing is when you're acquiring locks and locks and locks. You're growing with the number of locks you have. Shrinking is when you're releasing the locks. So in any transaction, it happens in two parts. First, once it grows, it keeps on growing. And when it starts shrinking, it keeps shrinking. It will never grow again once a transaction goes into the shrinking phase. So let me take an example. So this is server A. Let me take here. Now suppose there's a transaction. It acquires a lock on resource A. So we have lock on resource A. We'll mark it as plus A. Now it acquires a lock on resource B, that is plus B. So then it requires maybe a shared lock on C, exclusive on D. Now this is called the growing phase. Okay? Till now we are on the same page. We are growing, we are adding the number of locks. Now what happens when the shrinking phase starts? As soon as we start releasing even one lock, we will only lose the lock, we will only release the lock, we will never ever add any lock. So suppose we do minus A, that is release a lock. Now we can do minus B, minus C, minus D. Now this phase is called shrinking phase. So that's the difference. When the growing starts, you only acquire lock, and the shrinking starts, you only release lock. Now there's a point in which it moves from the growing phase to shrinking phase, this point. Now this timestamp, whenever this happens, we have a name for it. It's called lock point. So the point where the growing phase changes to the shrinking phase, it's called a lock point. Okay, now let's take a real-time example. Let me draw for you. So there's a bank server, and we'll draw some transactions. Now there's a transaction 1 that is happening of A transfers $100 to B. So there will be two transactions in here. One is A minus $100 and B plus $100. Now what if there's another transaction which wants to read the data? So we can call this transaction 1, transaction 2. So if it wants to read a data, it cannot do it in between, because if it wants to read the value of B, we cannot read in between. So what it will do, the transaction 2 will wait till this time. So it will wait here. And once this transaction is complete, then it will acquire the shared lock here and read. So what it will read is that B now has plus $100. So this is how it works. Just to tell you, when this transaction happens, it acquires an exclusive lock because there's an updation of data. So this is how it works, that the person or the transaction who is even supposed to read, they will wait if an exclusive lock is on hold. Let's take another example. So transaction 3 It wants to read data. So it wants to read A. Similarly, transaction 4 wants to read A at the same time. So this is simple. Transaction A will get a shared lock over A. Similarly, transaction 4 will get a shared lock over resource A, and then both will read the same value, not plus 100, minus 100 at the same time. That way, both the transaction can read simultaneously because it's a shared lock and it's not a exclusive lock. So this is how a typical two-phase locking happens. Let's go into a bit more detail about two-phase locking. Let me show you the types of 2PL. The first one is strict 2PL. Second is rigorous 2PL. And the third is conservative 2PL. We'll go each one by one. Strict 2PL. In this, we will hold all the X locks until we commit. So what will happen is, whenever a transaction is happening using the exclusive lock, we will hold it till the transaction has committed the values. We will not release it. So this is how the strict 2PL works. But there is one thing. This will not work for the shared lock. So this is where comes the rigorous locks. Rigorous 2PL. In this, we will hold all shared plus exclusive locks until the commit has happened. So now this is much more rigorous than the strict. In strict, we were only holding all the exclusive locks. In this case, we will hold all the shared and exclusive locks which we have acquired till the time the commit has finished, and we will not allow even a shared lock to be used by any other transaction. So this is why it is called rigorous 2PL. The third one is conservative. In the conservative lock, what we do is we primarily acquire all the locks which we require from the beginning, because there's a problem with rigorous and strict 2PL. For example, while doing some transaction, we've acquired new exclusive locks on the way, and there happens a time that we need a lock on server B, but the lock on server B is already being held by another transaction. And server B needs the lock which is acquired by server A. In this case, there's a deadlock. How do we solve them? So now what we use is conservative 2PL. In conservative 2PL, we acquire all the locks before even starting the transactions. Once we have the lock, then only we start the transaction. We just wait till the time we don't have all the locks. So let me write it down. Acquire locks till, okay, before transaction. That's how we do it. Now, there's one advantage of conservative 2PL over rigorous is that we can overcome the deadlock issue which we happen to have acquired using the rigorous 2PL or strict 2PL. But there is one very big flaw of conservative 2PL, especially, nowadays we have so many transactions, we need 1 million transactions per second. Because of the locks, the process becomes very slow. It's not concurrent anymore. It is now serializable, happening one after the another, because of which so many processes are waiting for their commit to happen before the previous one can finish. That is one of the drawbacks of 2PL, but still we are strongly supporting the asset properties of the database, that is atomicity and consistency. So this is how we can maintain the atomicity and consistency using the 2PL. So 2PL is a pessimistic lock, but it's very reliable to ensure safe concurrency. It should be used when we are using very critical systems that needs very strong consistency. For example, banking system, or maybe share market or stock exchange. But we also have an alternative for this. We have optimistic locks that can be used in some places but not in critical system. So that's it about 2PL. So if you like this video, please like, subscribe and comment your doubts and keep watching. Thank you for watching. Take care. Bye.